Welcome to This Explainer. Today, we're doing something really exciting. We are bridging that fascinating gap between abstract C programming concepts and tangible, physical hardware manipulation. If you've ever found yourself wondering exactly how typed lines of text somehow translate into real-world actions, like motors turning, sensors reading, or lights flashing, you are absolutely in the right place. So, let's jump right in.
Here's our roadmap for today. We'll start with the anatomy of C functions, move into math and logic operators, figure out how to make decisions in code, put microcontroller hardware into action, and wrap up by reading analog sensor data.
All right, first up, the anatomy of C functions. I want you to think of standard functions as mini machines within a much larger factory. They take specific inputs, they process them in a highly organized way, and then they perform a specific task or spit out a result. Every single program you write is essentially going to be a collection of these mini machines working together. But here's the catch. For the compiler to actually understand them, they have to be properly declared.
To build one of these mini machines, you've got to provide a prototype. This prototype tells the compiler everything it needs to know right up front. It gives the function's name, the formal parameters it expects to receive, and the exact type of result it's going to return. And hey, if your mini machine just performs an action, like flipping on a light, and doesn't need to return a mathematical result to the system, you simply declare its return type as void.
Now, there is one very specific, absolutely crucial word we need to talk about, and that's main. If standard functions are the mini machines on the factory floor, the main function is the factory manager. Every single C program has to have a main function, no exceptions, because this is exactly where the program execution always starts.
Moving right along to Section 2, Operators, Math and Logic. Operators are basically the action verbs of our code. We use standard arithmetic operators for everyday math, like addition or finding remainders. But when it comes to hardware control, it's the relational operators that are the real stars. These let us compare values. And as a quick refresher, remember that in C, checking for equality uses a double equal sign. A single equals assigns a value, sure, but the double equals is our relational question. It asks, are these two things exactly the same? Which is totally vital for evaluating sensor thresholds.
So here's a detail that trips up a lot of people. Timing is literally everything. Think about the difference between pre-increment and post-increment. It seems like a tiny syntax quirk, but it drastically changes how your physical hardware reacts. Pre-increment, which is ++a, adds 1 to the value before it's used in the expression. But post-increment, a++, uses the current value first and only increments it after. If you're counting the exact number of rotations on a stepper motor, mixing these two up is going to throw your entire machine way out of sync.
Let's shift gears to logical operators and see how they build our hardware logic. The strict logical AND, represented by the double ampersand, demands that both operands are true. Imagine a heavy, dangerous piece of industrial machinery. For absolute safety, the system might require the operator to press a button with their left hand and a button with their right hand at the exact same time before that machine powers up.
Then we have the OR operator, written with two vertical pipes. This one is way more forgiving. It returns a true 1 if at least one of the input operands is a 1. Think about a standard home security system. The alarm is going to sound if the front door is opened or if the back door is opened. It doesn't need both to happen to trigger the siren.
And finally, the NOT operator, denoted by an exclamation point. It simply flips the bit. It turns a true 1 into a false 0 and a false 0 into a true 1. Now you might think, when would I use that? It's actually used constantly in embedded systems, especially when you're dealing with active low physical buttons, where pressing the physical button actually sends a 0 to the microcontroller instead of a 1.
All right, part 3, making decisions in code. So a microcontroller isn't actually smart on its own, right? It's literally just a piece of silicon. It needs a highly structured way to evaluate the conditions we were just talking about, and then choose a specific path based on those results. Enter the mighty if-else statement. It flows so logically and predictably. The microcontroller checks a condition inside the parentheses. Is the condition true? Great, execute the code. Is it false? Skip right over it to the alternative block. It's the ultimate fork in the road for your logic.
But what happens when you hit a massive intersection with, say, 5 or 10 different roads? When you've got multiple distinct options to handle, like responding differently to 5 different physical buttons, the switch operator is your best friend. It provides a much cleaner syntax.
You just check your selector against your various distinct cases, execute the one that matches, and break out. It is so much better than stacking 10 if statements on top of each other and questioning your life choices.
Let's get to the fun stuff. Section 4. Microcontroller hardware in action.
To pull this off efficiently, we absolutely don't want to reinvent the wheel. We work inside environments like Micro C Pro. What makes this so incredibly powerful is the built-in library manager. It hands us these amazing pre-written libraries that let us easily manipulate the chip's hardware pins, entirely skipping the need to manually code every single tedious low-level register instruction. It's a massive accelerator for embedded programming.
And here is our hero code, the legendary Blink and LED program. Take a look at the logic. Inside our main function, we set trisb.f0 to 0. Tris controls the direction, so 0 means we're setting it as an output pin. Then we jump into an infinite while loop. Inside that loop, we set portb.f0 to a 1. That sends out voltage and turns the LED on. We wait 1,000 milliseconds using our library delay function, and then we set it to 0 to turn it off. It really is that simple. Well, assuming you wired the LED the right way around and didn't release the magic smoke, of course.
Once you've got that basic blink down, a whole new world of physical control opens up. You can start combining the if statements we reviewed earlier with real hardware inputs to create pretty complex patterns. Just imagine reading a 1 from a physical button on port B and using an if-else structure to reverse the direction of a sequential LED light show. At that point, you are literally commanding physical electricity using pure software logic. It's a great feeling.
And finally, Section 5. Reading analog sensor data.
Blinking LEDs is cool, but the real world isn't just digital ones and zeros. To read a nuanced sensor, like a thermometer that outputs a smoothly varying voltage depending on the temperature in the room, we can't just read a simple high or low. We have to look to the ANSL, or analog select register. Setting these specific bits to a 1 tells the microcontroller to stop looking for simple digital signals and instead prepare to read complex varying analog voltages on those exact pins.
Once the pin is actually prepped and ready, we use the ADCON register to manage the conversion itself. We select our exact input channel using the CHS bits, and when we are fully ready, we set the Go bit. Setting that bit triggers the internal hardware to perform an analog to digital conversion. It captures that real-world physical nuance and turns it into a discrete number that our C code can actually understand, evaluate, and act upon.
We've really journeyed from standard C syntax straight down to the bare metal of analog pins today. You now hold the keys to the bridge between pure software logic and physical electricity. But here's the real question. Now that you actually know how to translate a line of code into a physical action, what real-world problem is currently sitting on your workbench waiting to be solved? Get out there, keep experimenting, keep building, and thank you so much for joining me on this explainer.